Our next speaker is Lisa Hazard. Lisa is a Deputy Director for the Coastal Observing Research and Development Center. Lisa manages operations facilities and resources for a team of technical staff in the development and deployment of new technologies, their application and basic applied sciences. Lisa's going to talk about HF radar, I hope. We actually have a long history. It was, I don't know, it was after Costco Busan, whenever that was, that I really pushed hard for HF radar to be available to the public in a digestible format. In other words, you didn't have to seek it out and then know what to do with it to make meaningful use of it. And I'm happy to say that these days, HF radar is available from many sources. What I am most excited about it is actually within the IRMA data viewer. If you pull up IRMA, you can get all the HF radar data for California. So that would be IRMA Southwest. Anyway, Lisa's going to talk. She's going to give us updates on the national HF radar system. Okay, Lisa, it's all yours.
Great. Thanks, Jed. Much appreciated. All right, I'm going to share my screen. Let's see, and go into presentation mode. So how's that for everyone? Good?
Excellent.
Great. So yes, I'm here to talk about the high frequency radar network, which is the technology used to map ocean surface currents. And many of you may be familiar with this technology, but I will briefly touch on what it is and the products that you get out of it. In California, the array of systems, these green dots here, these points are all of the HF radar systems along the coast of California. And the network is actually operated by primarily academic institutions, using the data for research and looking at ensuring the quality of the information is accurate. We do have the CODAR ocean sensor is one of the technology manufacturers, helps oversee some of the sites in Northern California. And at the end, I'm sure the presentations will be available, but if there's any further questions, contact information is below. So briefly, just about the technology, these systems are a antenna-based system that sends out a radio signal across the ocean. It is tuned to the swell waves. The signal is received back to the antenna. And knowing the open ocean wave speed, there's a calculation for a wave speed. Any deviation on that is the current in which it's riding. So we can get surface currents to and from the antenna directly. So you'll see here, these are bands of currents binned out from one single antenna. And then you need a network, an array of those antennas to ensure you can have a true vector calculation. So the radars are spaced anywhere from 30 to 60 kilometers apart. Each system, depending on the frequency, you can get different resolutions. So you can have a low frequency system that resolves about a 5 kilometer patch of ocean, and a higher frequency system, say a 25 megahertz, and you get a 1 kilometer patch. So you get a surface current every 1 kilometer. I will say for oil spill response and trajectory mapping, the currents do start approximately 1 kilometer offshore. So you're kind of breaking through that surf zone and getting out into open ocean for those surface current measurements. The network has grown significantly since its inception, which was first funded by NOAA, picked it up in 2004. So there are now 173 HF radar sites operating throughout the US, in Puerto Rico, in Hawaii and Alaska. There are 7 national portals, operating HF radar operating organizations. So most organizations oversee the operations of about 10 or so systems, 5 to 10 systems. Those data feed into portals, and then there are 2 operational nodes that basically bring in that radial data that you saw from one site, aggregate and produce the surface current vector maps. Over here on the right-hand side is basically sort of a cartoon depiction of how the data gets from the site into an aggregator or portal, we call it, and then into the operational nodes at Scripps Institution of Oceanography and at the National Data Buoy Center. This particular depiction also shows the data's pathway for getting into the US Coast Guard Search and Rescue optimal planning system. And yes, the system has been in operation for 17 years now. And there's been a national radar plan adopted in 2009 and updated in 2015. So just to look real briefly at the history of the national network growth, again, there are a few systems that were operating actually in San Diego and Santa Barbara channels prior to sort of this statewide investment within California and national investment in the kind of aggregation of the data. And so this burst right here is actually the California investment with state funding through the Coastal Oceans Currents Monitoring Program. So I figured I'd throw in some pictures of what the sites look like and some of the supporting infrastructure. So we have these antenna systems close to the shore, and clearly they undergo a lot of weather and elements. We have solar panels for some of the sites. Some of the sites are mobile, and of course, communications connecting all of the information together. This system is down here at the most southern site at Borderfield State Park. So one of the, in maintaining these systems, they do require calibration. And what that calibration is you want to see if there's any deviation of the antenna's signal response from, if there's other metal or things around can modify what the signal response looks like to the antenna. And so historically, we drove a boat in an arc around the antenna system, where over the few decades, things have improved. We've seen a lot of autonomous vehicles and drone technologies take root, and we're actually using those technologies to calibrate the systems as well. So you basically fly an arc around the entire system and see what that response function looks like. Up here, just kind of some of the weathered systems and maintenance required on the antennas and infrastructure. And this line plot in the middle shows sort of a kind of latency. You get data on the order of about an hour as the data is processed and fed into the network. So the goals of surface current mapping is to provide these maps and make observations and products to the large community of managers, planners, operational decision makers, scientists, and the general public. And so we want to make sure that this data is available, accessed, and used. And so sort of on the order of the marine operations, navigation, search and rescue, obviously oil spill response, renewable energy, and any coastal hazards, climate variability, ecosystems, and water quality. And I'll kind of get into some of those a little bit, just to show you some use case scenarios outside of, within and outside of oil spill response. So again, kind of going off of the themes, some of the stakeholders, especially here in California, we have NOAA uses the data, it also supports it and then brings it back in for their own uses. Of course, the Coast Guard we've mentioned, and OSPR and BOEM, And then a lot of local agencies, so dischargers have used the data extensively during some outfall discharge industry, and of course the public. Been in touch a lot with the public on primarily on water quality issues. And again, we'll get into that a little bit. So as Jed mentioned, the data for OSPR and oil spill response, we have the data going to the operators of the GNOME model that produce the trajectories. So many spill responders may not even know that they're actually, benefiting from the use of HF radar surface current maps, because they're getting those operational data from the GNOME model, and that's being used as a check and balance system to ensure the currents are correlating with the trajectories. And as Jed mentioned, also all forms of the HF radar data are available through IRMA. And so we had always supported a format specifically for the GIS folks, and then we're able to transition this over to IRMA. So I mentioned early on how depending on the antenna frequency that you're operating, you get a different resolution of your surface currents. So you'll see that there are, I know it's difficult to see in here, but you get a 1 kilometer resolution, a 2 kilometer resolution, and a 6 kilometer resolution. So depending on sort of your what you're looking at, and what the lower frequencies extend much further out. And so you're getting a bigger footprint and a bigger coverage area, but you're losing that resolution piece. So within Southern California, we do tend to have higher resolution systems because of the impact to the coast. So kind of getting into some other applications, I thought it'd be interesting, particularly, and you can kind of project this onto oil spill response as well. What you see here are exposure maps. And what the exposure map is the probability of exposure at a point of something coming through and infecting through the coastline here. And again, I mentioned that the surface currents start around 1 kilometer offshore. So you have to be a little bit cautious of your near shore transport. You may get, kind of like a longer transport in either direction. We've done a lot of work actually at the border, and oftentimes the currents do mirror the coastline, but you can definitely have deviations. So what you're seeing here in these different panels are percent exposure. So from 100% in red, so you'll definitely be getting exposure from water particles coming and infecting out, to 1% in blue. And what you can see from these different panels is that depending on the time, and these are literally different days, you can have a very tight impact. So if you have a spill, it could stay like very localized, or depending on the currents and what's happening, you could have like very widespread impact. And so you really have to be aware of these circulation patterns and the currents to know kind of that impact. And again, this is looking at sort of water quality and some areas of discharge. In these lower panels, similarly, these are at 3 different locations in California, and the different columns represent an annual feed, an actual storm event, and then another day following this storm event. And so you can just see how these can vary quite broadly depending on what the conditions are happening. So it's good to sort of look holistically. At the border, we actually run a plume tracking method where we seed the first surface current vector just offshore of the Tijuana River, and constantly keep track of that. So this is days of the particle age. And so, these dots are sort of the sampling locations for water quality. So you can see as we track what the particles are doing within the surface current vector field, we get a sense of where those particles and where that water may be flowing. And the reason for this is oftentimes during discharge and flow, this is highly contaminated water. On an alternate space, over to the right, during discharge, the color now represents depth. And so what we're looking at is different surface, and so we had a mooring here, so we can track the currents at depth and see how widely the surface currents, you'll see over in Hyperion, the surface currents are really affecting the coastline, but at depth, it's more offshore. So similarly with an oil spill, when you're getting that surface current layer, your oil is transporting and advecting and hitting other areas. And I know when you disperse and send things, in the water column, then it may go in a different location. I threw this line plot up here. Actually, we used the surface currents plus our automated identification system recently. The dischargers at Orange County had their mooring hit and dragged. So you can see sort of this defined, so we're looking at it from the surface currents, where could it be going, and then correlated that with the AIS plots to help them locate their lost buoy. Other areas of where surface currents are used in model assimilation. So we're getting a lot of improved modeling capabilities with the surface current addition of the real-time data, giving that sort of input into models. And this is a very kind of modelers have been looking at integrating the total vectors, but then also now we're getting into having them actually integrate at the radial level. So one step prior to the surface current maps. And then they can do their own vector calculation within the model. So that's kind of an emerging field that's happening right now. Also, using surface currents to overlay satellite maps. This is pictures of a bloom from last year, and kind of overlaying some of the surface currents. This is just a snapshot. So if we were to take sort of a movie, you'd probably be able to see and follow some of these eddies as the surface currents really track kind of what you're seeing from the satellite. So kind of nice use of comparing information and data. Just kind of wanted to highlight some of our outreach. We're in the aquariums, we're have people at the piers looking at systems offshore, and really making sure getting the information out and working with users and the general public. From a California perspective, just sort of from a climatology and information, just kind of wanted to showcase the West Coast and how the investment of the state has really ensured that we have really great coverage for our surface current mapping fields, and that we've been able to maintain this network and keep it going. We do need to update some of the systems as they're aging, but it's been great to be able to maintain this information. So I thought I'd get into a little bit, again, just kind of highlighting how the data flows. So here you have the radial file, which goes to a portal, then goes to a node server. These radial files are combined to create that surface current vector map. We do keep a performance metric. So basically how looking at each radar system, ensuring that data is getting into the network within a 25-hour time frame. Again, usually you have about an hour lag, but in order to reprocess the data, we ensure that those data feeds are getting in within 25 hours. Some diagnostics, we look at how the data is coming in, what our ranges are, and whether it's a calibrated or non-calibrated data field. So how do we distribute the data? So we have an online visualization. We allow web overlays for individuals who want to actually code the data into their own software, which is what IRMA's doing. Through the, we have a thread service to get to the, this is the mapping service, thread service to get to the numbers, and a additional visualization where we display the 7 days in a KML file. And again, this image is kind of really highlighting that 1 kilometer higher density data versus the 6 kilometer data. So on the website, you can get to all of this information, and you can also not only look at the hourly data, but look at a 25-hour average. So you sort of get just like where the flow is going from a general sense. And again, can drill down into the different products, the different resolutions. This is just a snapshot of our 7-day KML version that you can bring in, so you can, access that on your own computer. Our thread server, if you're not a coder, my eyes glaze over, but it's all accessible for programming, and we have some demonstrations and some code repositories for access. The data are primarily distributed in NetCDF, and what you get is this URL request. And yes, I'm wrapping up. I know I have 4 seconds left here, but so anyway, just showing that we can have that NetCDF subset. And I just want to say thank you. I am certainly not the only one involved in this operation. I mentioned the principal investigators at the beginning, and this is a list of the actual operators who are out in the field maintaining these systems.
All right, thank you, Lisa. That was excellent. It was just what I was hoping to hear. I'm going to defer to Jenna for questions, but before I have a question myself. Okay, let me see if I can phrase this right. Are there any new initiatives that the HF radar scientists see as uses for the data?
Yeah, thanks for asking, Judd. So we actually, I know that there's been some discussion about, autonomous vehicles and sensing and what they can do. And we're looking at using those autonomous type systems, wave gliders, to mount, kind of looking at more on the HABs side, but obviously translate to oil spill as well, mounting, sensors and whatnot, and using the surface currents to be able to help drive that vehicle and map out where those, blooms are occurring with using the surface currents and the vehicles. Similarly, we're looking at a reanalysis product. So taking these, almost getting up to 2 decades of data and really doing a deep dive and looking at all of the, the trends. I know in San Diego, we have some very consistent eddies. And so in the oil spill response plan, we've located and identified where those eddies are. So even if you don't have any data, you can say, well, based on this, based on what time of year we're in, normally an eddy spins up. And so we're going to kind of see this sort of like current map. And so we have these consistencies. And I think doing that across all of California will be something that will be really interesting.
Okay, excellent. Thank you.